Bigtable and HBase were one of the first NoSQL databases designed for large-scale batch processing, essentially, and therefore didn't really have strong support for indexes. Recently, the database called MongoDB has become very popular because it does, in fact, include significant support for indexes. Instead of records, MongoDB uses the term documents, which are essentially structured documents. So they look a lot like records, but they can be more complex than records in the sense that one might have multiple titles or multiple categories, for example, in this case. This is sort of like HBase records because HBase can also have multiple values for a particular column. Like HBase, it's a sharded database so that documents or records are kept in different shards on different processors so that a set of keys goes to one shard. Additionally, just like HBase, we have 3 replicas for each shard. MongoDB, however, doesn't rely on the underlying distributed file system like HDFS, but keeps track of its own replicas in a manner reminiscent of traditional parallel relational databases. The underlying file system can be any operating system file system like Linux file system or something else. Further, the indexes that MongoDB supports include full text indexes so that it essentially has support for inverted indexing, as we saw in the first week of this course. Lastly, it also supports a form of MapReduce within the database itself. So one can effectively write MapReduce programs which process data in MongoDB using JavaScript, which is the only language it supports. Another important feature of MongoDB, which is shared by some other NoSQL databases, is its consistency model for writes. Recall that in HBase, for example, a write relies on a write to the distributed file system, which essentially completes writing a record only if all 3 replicas write successfully. This essentially makes writes into both GFS, HDFS, as well as HBase rather costly because it relies on all 3 replicas agreeing before a write succeeds. It's quite okay for large bulk writes, but doesn't quite add up for smaller writes or random writes because the extra overhead of making sure the replicas are consistent is relatively high for small operations. So instead, MongoDB uses something called eventual consistency, where writes or updates are propagated to replicas eventually and not synchronously with the write. So it's possible for a write to complete without all its replicas having been updated with that write. The first database to use eventual consistency was Amazon's SimpleDB, where the idea of vector clocks was used to achieve eventual consistency. Other NoSQL databases such as MongoDB also use vector clocks, so this is quite an important concept, and we'll illustrate it through an example. Each record is represented by a key, which could be, for example, the transaction ID or something else, and it needs to get replicated at 3 different replicas. In Amazon SimpleDB, for example, these replicas are chosen by hashing each key and essentially distributing the hashed values in a round-robin fashion to different physical nodes. A different replication technique is used in MongoDB, but that's not relevant for the vector clock discussion. Nevertheless, let's assume there's a record which is mapped to 3 physical nodes, x, y, and z. And now let's see what happens when we try to write a record which is replicated at 3 locations. Suppose we happen to write this record at x. We associate with that a timestamp 100. So this is a vector timestamp consisting of 3 elements, which tells us that this was written at timestamp 1 at physical node x, and the timestamps at the other nodes are maintained as 0. Next, we may want to write it again at physical node x, in which case we simply update the vector timestamp to 200 and forget about the old 100 version which was written earlier. That's because in vector terms 200 is greater than 100 in that at least one of the terms is greater than the one in 100 and the others are at least equal to the same in this vector. On the other hand, suppose we were to first write at location x, and the next write for some reason happened at location y, just because of parallelism. The vector timestamp for this write would then be 010, because the value it is writing had timestamp 000, and it's writing it at y, so it is assigned a timestamp of 010 now. Next, this write is propagated to all the replicas. Both writes are propagated to the other 2 replicas, so x gets the value from y, 010, y gets the value from x, and z gets the value from both x and y. Now, in each of these cases, neither of the 2 values of our record are greater than each other in vector terms, so each replica has to maintain both values until something more interesting happens in the future. For example, now if we read the value z, where we read both these replicas 100 and 010 from the location z, and now we do some computation and write a fresh value. Because we read both these replicas with timestamps 100 and 010, figured out which one to use using some application logic, and then wrote a value. The value written has a timestamp 111 because it's based on values that have seen 100 and 010 as timestamps. Now 111 is greater than both of these, so the value written overrides the previous 2 and they can be discarded, and when this value propagates to x and y, the corresponding older values also get discarded. As a result, what we achieve is eventual consistency, in that at some point of time when you read a record, you might get 2 values instead of just 1 because you're getting an inconsistent state, and it's up to you as the application to resolve that inconsistency, usually using some knowledge of what these values are all about. For example, suppose the write is essentially adding another value to the record. In this case, the previous 2 values simply need to be added together, to which a third value might get added, and that inconsistency is well resolved because none of the previous writes is actually thrown away, but they are actually summed up by the third write. A second example might be where the write is a blind write, which doesn't really care what was written in that record earlier, in which case it doesn't really matter which of the previous two one needs to choose because they are ignored in any case. And the third write simply writes and resolves the conflict by assigning a higher vector timestamp. The final case is the most complicated one, where the write depends on the previous value, such as a update. So suppose you're incrementing the value of a record, perhaps by different amounts each time. So you have to choose which of the previous two versions you want to use and do this consistently so that the second time this kind of a conflict occurs, the rule applied is the same. What is typically done in such situations is you use a lexicographical or alphabetical ordering of the replicas so that, for example, the replica X is treated as higher than the replica Y, which is treated higher than the replica Z, so that while choosing between 100 and 010, the third replica chooses to use this value timestamped with 100, increment it with whatever it chooses to do, and then write with the timestamp 111. Since we use a consistent ordering of the replicas by alphabetical order of some kind, we will always get consistent results. Now, it's not that obvious, and the theory of vector timestamps dates back to the 70s in classical work by Leslie Lamport, and the original paper is really worth reading. The paper itself is from 1978, and there are some previous versions of it, but the most accessible one is this one, which appeared in the Communications of the ACM. The theory of why a lexicographical ordering works always is elegantly put in this paper, and interestingly, more than 30 years later, we are seeing this concept being used for eventual consistency in multiple NoSQL databases: Amazon SimpleDB to start with, MongoDB, CouchDB, Cassandra, and many others.